Namaskar, good afternoon, good morning, good evening, depending upon which part of the world you are. आप सभी का PRL के अमृत व्याख्यान में स्वागत है, अभिनंदन है. A very hearty welcome from me, Anil Bharadwaj, for the PRL का अमृत व्याख्यान. This is the 8th व्याख्यान of the 75 episode series of व्याख्यान्स, which is being organized as a part of PRL's 75 years of legacy and history in fundamental physics and space sciences. Established in the year 1947 by the father of Indian space program, Dr. Vikram Sarabhai, the PRL's Platinum Jubilee coincides with the India's 75 years of independence. Hence, it's a joint celebration of development of science and technology in India by PRL under the banner of PRL का अमृत व्याख्यान. Today's व्याख्यान is being conducted as a celebration of the foundation day of Udaipur Solar Observatory of PRL, which happens to be on 20th of September. Hence, today's व्याख्यान is a very special व्याख्यान, and hence we have a specially distinguished speaker for today's व्याख्यान, Dr. Valentin Martinez present. Dr. Valentin is the director of National Solar Observatory in USA, in short NSO, and Udaipur Solar Observatory and NSO has a very long partnership since 1992 in the GONG project, which is basically the Global Oscillation Network Group. We have already completed more than 25 years of this long partnership, and we are fortunate and thankful to Valentin to accept our invitation and be the speaker of the Vyakhyaan today. So thank you, Valentin, for accepting our invitation and being a part of PRL's Platinum Jubilee celebration, as well as PRL ka Amrit Vyakhyaan. So thank you all, and over to Nanita.
Thank you, Professor Bharadwaj, for welcoming our guests for this special lecture or Vyakhyaan of today. I now invite Professor Shibu Matthew to introduce the speaker of 8th Vyakhyaan, Valentin Martinez Pillet. Professor Shibu Matthew, please.
Yeah. Dr. Valentin Martinez Pillet is a well-known solar physicist. He is currently the director of National Solar Observatory, and he is stationed at Boulder in Colorado. The NSO operates the largest solar telescope in the world, the 4-meter DKIST, which became operational in 2019. Dr. Valentin joined NSO as the director in 2013. He oversaw the installation and commissioning of the DKIST. Before he started his career in NSO, he was a senior scientist at the Institute of Astrophysica, Tenerife. In IIC, he was the PI for the imaging magnetograph experiment, that is IMAX, for the 1-meter sunrise balloon-borne experiment. He is an expert in solar polarimetry, and he worked with some of the best telescopes in the world. Now he is the co-PI of Polarimetric and Heliospheric imager instrument that was flown on the European Space Agency Solar Orbiter mission in February 2020. He is also a member of the science working team of the ESA-NASA Solar Orbiter mission. Valentin was the president of the Division 2 of the IAU, the Sun and Heliosphere from 2010 to 2012. He has also served as a member of the editorial board of Solar Physics Journal. Valentin published more than 250 research publications, reputed journals, and more than 25 invited review articles. He is also a member of several international scientific bodies and member of scientific advisory committees of various institutions of international repute. So with these words, I invite Valentin for the over to Nandita for inviting him.
Pillet.
No, I
to
think
deliver.
you're muted.
Sorry, can you hear me?
Yes.
Okay. So I now invite Dr. Valentin to present the 8th Vyakhyaan of today, and we are looking forward to this lecture as it is a very special one on our Foundation Day. Thank you very much for joining us and honoring us by giving this lecture. Over to you, Valentin.
Thank you very much. I'm going to start sharing my screen, but first of all, I want to thank them for the invitation to give this 8th PRL Vyakhyaan. Yes, I think we are also commemorating the anniversary of the Udaipur Solar Observatory, and it's been said already, Udaipur and the National Solar Observatory have had a long-standing partnership for 25 years. As you'll see in my presentation, we are having plans for continuing these collaborations for additional decades, and you'll see it at the end of my talk. My talk here, you have the title, Prospects in Solar Physics for the Next Decade, a Multi-Messenger Era. It's going to have three parts. Part number one, what I call magnetic connectivity, the multi-messenger decade, is about setting the stage of the science that I think is going to dominate solar and heliospheric physics. And then I'll go into giving an update on the two facilities that are being built or operated by the National Solar Observatory. I'll be giving an update on the Daniel K. Inouye Solar Telescope, but also about the GONG and the future of GONG that we call NG-GONG, where we're hoping that Udaipur will also play a role. Let me move on into the first part of my talk. This slide in here represents the overarching theme of what I want to talk to all of you today. As I said, here is magnetic connectivity, but really another way of putting the same question is how stars and planets are magnetically connected. And this is important in many contexts. For example, if you go to the image on the left, we know that this is important, this magnetic connectivity, for understanding the drivers of space weather. Space weather is something that is important, that we try to monitor and we try to predict today, and you'll see the state of the art during my presentation. But it is an area of research that is only a few decades old, and where we are getting quantitative data and an understanding of the physics that is behind. Here in this image that I have on the left, you'll see that I have some yellow magnetic field lines that are coming out from the sun, and I have the magnetic field line from the Earth. If you see, the way I draw them is that they are anti-parallel. The magnetic field from the Earth is pointing upwards. The magnetic field coming from the sun is pointing downwards. This magnetic field from the sun is what comes out after an explosion, typically a flare. Then there is some mass that is ejected from the corona. We call them coronal mass ejection, CMEs. And only since the last couple of decades or so, we know that what is important is being able to predict what is the orientation of the magnetic field coming out from the sun, whether it is anti-parallel to the magnetic field of the Earth or parallel to the magnetic field of the Earth. Only when there is this anti-parallel configuration that we have here, do we get the greatest, the largest, the most influential geomagnetic storms and the greatest impact on our civilization, on our technological civilization. If the magnetic field from the sun comes parallel, the effects are minor. I want to emphasize this, but what I think is important is that this is knowledge that we have acquired only over the last decade or so. At the beginning of the century, it wasn't that clear how important that orientation it was. We now know that this is a key factor that we need to start predicting with our modeling. Here on the right, what I'm showing is that this connectivity between stars and planets is not only important for the Earth, for the space weather here on planet Earth, it's also important beyond our solar system. And we now know that the habitability of some of the planets that are orbiting stars, brown dwarfs, like the case of Proxima Centauri, and that would be a picture of Proxima Centauri together with Proxima b. Proxima b is a planet that is relatively close, and it is in the habitability zone, so it probably has water. But we also know that the large activity of the parent star of Proxima Centauri will make this water radioactive. So the living conditions, what type of habitability you can have on this planet is going to depend strongly on this magnetic connectivity. So as you see, this issue of the magnetic connectivity has practical aspects like space weather on Earth, but it also goes beyond the solar system. It extends to exoplanets. And I think this is another area where the solar physics is going to do this Rosetta Stone role that has traditionally done in astronomy. So in this slide, what I have here is the state of the art of this space weather prediction of this magnetic connectivity. What you see here on the circle over here is a view from the heliosphere from the top. This is the Earth, this is Venus, this is Mercury, Mars over here, and the Sun here. During this animation, and this is actual data, it's driven from data, you see 5 coronal mass ejections that are coming out of the Sun. The first one will be hitting the Earth, which is in here. The other 4 are going to go in this direction, and it's actually going to hit this spacecraft stereo A. Here you have 3 of them hitting stereo, and then there is a fourth one. What I like to emphasize is that these coronal mass ejections are propagating in a background magnetic field. The background magnetic field is this spiral that you see in here. We call it the Parker's spiral. This Parker's spiral here is modeled from data from the GONG station, and here you have a GONG magnetogram. So this type of magnetograms and the magnetograms from the other 5 stations are used to model the background spiral that you see in here. So you can actually go to the model here and investigate what is the magnetic field, what is the prediction for the magnetic field through this Parker's spiral is where we have the solar wind. The sun is always emanating particles. Sometimes it's in a relatively smooth way, and that's what we call the solar wind. Sometimes it's more episodic and more explosive. That would be a coronal mass ejection. So this background field is magnetized. It's coming from magnetic data, and we can make a prediction of what the magnetic field is going to be. However, for the CMEs that you see in here, we're not yet ready to predict what is the magnetic field of the CMEs. We cannot tell whether they are going to come parallel or anti-parallel. And I just mentioned in the previous slides that it is important that we're able to predict that. But we're not able to do it. These models, this is modeling from NOAA, from the Space Weather Prediction Center in Boulder, that uses GONG data and makes these predictions, but the CMEs are not driven from magnetic data. Now, one of the things that I want to say from this slide in here is, look what happens to stereo A. It's going to be hit by 3 CMEs. When the 3 CMEs hit stereo, it's really hard to tell what is coming from each one of the CMEs. Stereo is going to have a hard time understanding these particles are coming from that CME and these particles are coming from that other CME. And this is because stereo is at 1 AU. So the only way in which you can understand what each CME is doing is by getting closer. By getting closer to the sun, you'll be able to isolate one CME and understand, okay, that CME coming from that part of the sun produces this type of consequences in the heliosphere. So getting closer is crucial in terms of isolating the different processes going on in the heliosphere. And this is the reason why some time ago already, ESA and NASA decided to come up with these 2 missions, Solar Orbiter and Parker Solar Probe. Both have one thing in common. They are both getting closer to the sun for the reasons that I just explained. Parker Solar Probe and Solar Orbiter are measuring in situ the consequences of all these processes happening on the sun. They measure in situ with particle detectors, with magnetic and fields detectors. And what we want to do is all these in situ measurements, how are they originated on the sun? How is this magnetic connectivity translated into solar processes? But then we need to observe these solar processes. And for observing the solar processes, we're going to have a number of possibilities. But the one I want to outline here is that the Daniel K. Inouye Solar Telescope on the island of Maui is going to start operations in a couple of months from now. This is DKIST over here. Of course, I'm going to emphasize these 2 space missions and DKIST because of the multi-messenger components that they enable, and I'll explain them more during my talk. But of course, all of this suite of other space missions and ground-based telescope also play a role, of course, including GONG. I already mentioned GONG, and I'll keep mentioning examples of what GONG can do. I also want to say that a smaller telescope like MASS, that is at Udaipur, can play a role in terms of their availability for precise measurements of the magnetic field, while the telescopes have less demand in terms of proposal pressure from the community. So there is a role for all of them in this multi-messenger decade. What I want to do now is to explain why am I using the word multi-messenger. Of course, the reason is because there are multiple messengers. That's what is reflected here with Parker Solar Probe and Solar Orbiter, and here you have the launch of both missions. We're measuring different messengers. We're measuring particles from the solar wind, particles from energetic processes. We're measuring electric and magnetic fields. So these are the two messengers, and what we want to know is how they were originated on the sun, and we want to be able to observe them with telescopes and find what I'm calling here the electromagnetic counterpart. It is this combination of telescopes, remote sensing, and the electromagnetic counterpart versus the particles and the magnetic field that you measure in situ, what I'm calling multi-messenger. A number of colleagues and I wrote a white paper on this multi-messenger decade. Here is the link in case you want to see the science cases that this multi-messenger decade is going to enable. I'm going to just mention two of them. Solar Orbiter was defined as a multi-messenger mission from the beginning. And the reason is that it has a suite of telescopes, but it also has in situ instruments. And some of them are coupled in the sense that it is important what you measure with remote sensing versus what you measure in situ. For example, you have the SPICE telescope. The SPICE telescope is a spectrograph that tells you the chemical composition on the sun. It is a spectrograph. But then you can measure with the solar wind analyzer the local composition in situ. If the chemical composition on the sun and in situ are the same, you probably are measuring what occurs in the sun and the consequences in situ. And that allows you to make more quantitative this connectivity, this magnetic connectivity. Another suite of instruments that are coupled is the polarimetric and heliospheric imager that's going to measure the magnetic field wherever the spacecraft is. Sometimes solar orbit is going to be on the far side of the sun where GONG or from the Earth, we cannot tell anything. They're going to have a magnetograph, and they're going to produce this Parker's spiral, this modeling of the heliospheric magnetic field. And then the local magnetic field will be measured by the magnetometer on board. And we can compare the predictions from what we are modeling from the sun versus what we measure, and then correct if there are errors. So here you see beautiful combinations of multi-messenger science by remote sensing and in situ type of measurements. For Parker Solar Probe is similar. Parker also has a telescope that is looking only at the side of the spacecraft. What I want to emphasize here in this talk is that Parker Solar Probe is measuring particles, particles from the solar wind or energetic particles, but it's also measuring fields, magnetic fields, and this I'm going to be explaining what the findings from Parker have been. Of course, what is interesting about Parker is that it's really getting close to the sun because it's much closer than Solar Orbiter. It cannot have complex instrumentation, but the few instruments that it has are really unique. Parker Solar Probe is going to get closer to the region where the solar wind is being accelerated, the Alphen radius, and that's going to be really, really unique. It's getting closer, and you will do this over the next year or so. So let me show this result, which is the first outstanding result from the encounters that Parker has been doing. What Parker found is reflected here. So if you are measuring locally the magnetic field, you'll measure we were expecting to measure the Parker's spiral. The Parker's spiral is this envelope over here. If you are on the south part of the magnetic equator, the heliospheric current sheet, we're expecting to measure that part of the curve. If you are above the magnetic equator, you would be measuring that part of the curve. And Parker kind of measured that. Here it measured the top part, and then it crossed the magnetic equator and it measured the bottom part. But at all times, it measured this forest of magnetic field fluctuations that go almost to have the opposite sign. This is what it was termed as switchbacks, and these are the two papers that describe the discovery of the switchbacks with Parker Solar Probe. You have here a cartoon of the type of magnetic field fluctuations that are indicated by the switchbacks. This would be like the magnetic field turning 180 degrees from the direction it has. And what is important here is that to bend the magnetic field lines in this way, you have to do work. You have to do work against the magnetic field, meaning that someone is releasing energy. And if you release energy, you might be heating the environment. And as you know, coronal heating is one of the biggest unknowns in solar physics, how the corona gets heated. And then, of course, the question is, are the switchbacks some form of smoking gun from the coronal heating processes? So that's what we're trying to understand from Parker. And this is intrinsically a multi-messenger problem. Let me show why. There are two possibilities that have been proposed for explaining the switchbacks. I am going to concentrate on the first one, which is that they originate in the solar atmosphere close to the surface, and then they propagate outwards. If that's the case, this is really an intrinsically multi-messenger problem. Another explanation that has been provided is option 2, which is the evolution of the expanding solar wind. The evolution of the expanding solar wind will be less of a multi-messenger problem, but it really depends on what do we mean by the evolution, and we don't have a clear understanding of this second option yet of how is this being proposed to occur. But option 1, which is that they originate in the solar atmosphere, is better understood in the sense that the physical process giving rise to switchbacks has been proposed and is something that actually has been thought of to exist on the sun for actually decades. It's called interchain reconnection. The whole idea is that there is this open magnetic field line that you see here. The solar wind will be flowing through it. And then the open magnetic field line will interact with a closed loop, and this closed loop in here. Because of the opposite orientations, then it will reconnect. And through the reconnection, it will create this bending of the magnetic field line. This would be the switchback that then it will propagate and be carried out with the solar wind. So that's what Parker would be measuring. But then how can we tell that this was created on the sun? Well, because the prediction here is that opposite magnetic polarities are going to meet together and they are going to interact. And through the reconnection that will release energy in the solar corona, you'll create the switchback that then propagates outward. So do we see these opposite polarity interactions on the sun? The answer is we have observed opposite polarity interactions of magnetic patches for decades on the sun. What is important, what I want to emphasize is this example that I have in here. This one is from SDO, HMI, is measuring magnetic fields. Black is one polarity, white is different polarity. And from this picture in here, you will say, well, there is not much interaction. Black patches and white patches are separated. They are not touching each other. This is the same patch observed with IMAX sunrise. And now you see that there is a lot of small scale interactions when you have better resolution, spatial resolution, and sensitivity. And this black magnetic patch over here has nearby white patches that are interacting. And the question is this what it is, this interchange reconnection that even generates the switchbacks? We call this magnetic cancellation when black and white are interacting together. It's been observed for decades on the sun. It's been proposed for other type of energetic processes, like this case in here, where here the polarities is this red and the blue. And in here it was proposed for explaining how type 2 specules were created, again, related to energy release that potentially can hit the corona. What is important, what I want to emphasize is that there are two papers that are actually in press that have studied, these are the switchbacks from Parker Solar Probe. And they have studied the spatial distribution of the switchbacks. And what they found is that the granulation, the granular scale and the supergranular scales are detected when one's analyzed the occurrence of these switchbacks. Actually, this reconnection, this cancellation processes, interchange reconnection, is expected to occur in the boundaries of supergranules. So we're not surprised that supergranular scales are detected. And granulation is the main driver of foot point motions of magnetic fields. So there should be an imprint of granular scales too. There is this paper by Farged et al. That actually has detected both of them. And it's not the only paper. Stuart Bale, the PI of the plasma analyzer on Parker Solar Probe, also has a paper saying that they also detect the supergranular scales. But not only that, they also detect that when there is a switchback, they have an enhanced helium abundance. And I'm now going to move into measuring helium in the solar corona, in the solar wind. It's very important, and you'll see why. And you'll see that this is also another multi-messenger problem. Here, this figure, I don't know how well you can see it, but I'm going to explain it. This is time, and this is the solar cycle. So this is maximum, and this is minimum. And what you have in here is the speed of the solar wind, how it changes with solar cycle, the helium abundance. In here is helium abundance. And then during solar minimum, these curves in here change a lot from solar minimum to solar maximum. These are low velocities in the solar wind. These are high speed velocities on the solar wind. High speed velocities, fast solar wind doesn't change in terms of helium abundance that much, but the slow solar wind changes a lot. We don't understand what is the physics behind, but there is a clear magnetic dependence on the helium abundance on the solar wind. The more activity on the sun, the more helium we do see, and during solar minimum, in the slow solar wind, we do see very little helium, to the point that actually if you go to this curve and say, okay, when you go to 0 helium, total helium depletion, what is the velocity that you get? The velocity that you get is 250 kilometers per second, which actually is the minimum speed observed in the solar wind. So somehow in the sun, you get the fast solar wind with a lot of helium, but then if the velocity is smaller and smaller and smaller, it's because there is less and less helium on that solar wind. And keep in mind, the switchbacks are enhancements of helium. So we need to understand what is the physics behind. We don't understand what is this solar cycle dependency. It might not have anything to do with the switchbacks, but it is very clear that the helium abundance tells us a lot about how the solar wind, the fast and the slow solar wind, originates on the sun. And yes, Parker Solar Probe is measuring the helium abundance over specific regions on the heliosphere close to the sun. And the question is, can DKIST and Solar Orbiter say something about helium abundance in that source region? DKIST, Parker, and Solar Probe are going to have very interesting combinations during the orbits of Parker and Solar Probe. DKIST is here. This is again the heliosphere. This is the sun. This is the Earth. And in this encounter that is going to happen in 2024, we're going to have Solar Orbiter on the same line of sight as the Earth and the sun. Parker Solar Probe, however, is going to be at 90 degrees in quadrature. So with DKIST, and I will explain that DKIST can observe the solar corona with unprecedented capabilities, we're going to be observing the solar corona on the west limb in here, where Parker is measuring actually what is coming from the sun. There is also a coronagraph on Solar Orbiter, METIS. So METIS can also be observing the solar corona. So the two together can be observing the solar corona, and we can relate the observations, the remote sensing that Solar Orbiter and DKIST are going to do with the measurements of Parker, again, the multi-messenger connection. How are we going to do that? Well, with Solar Orbiter, we have an instrument that is Inouye that has an imager that will measure helium-2, helium-1 times ionized, and we'll measure also with a different instrument, with the coronagraph, METIS, hydrogen. So we can get this ratio and compare with the in-situ measurements of Parker. We can do something similar with DKIST. We don't know for sure how good this is going to play out, but we're going to try. DKIST can measure the solar corona. DKIST can actually measure helium, neutral helium in the solar corona. We know that there is this diffuse coronal helium brightness. You might be wondering how you want to have neutral helium in the millions degrees solar corona. We don't know, but it's been observed. One of the solutions that was proposed by Jeff Kuhn is that actually the solar wind, the ionized helium, alpha particles, and 1 times ionized helium interact with dust. And through dust interaction, which is getting sublimated as they get closer to the sun, you get free electrons and you get neutral helium. That has been hypothesized as the origin of this helium diffuse coronal brightness that has been observed. So we are able to observe helium, neutral helium, and if we're able to observe, as we can do with Cryo Earth, with DKIST, the hydrogen 1 of the patient series at 1.28 microns, we can also get the helium to hydrogen ratio and compare with what Parker is measuring. And that will tell us whether we see the same type of fluctuation between solar minimum and solar maximum. And what we hope is that we are able to see traces of indications of the switchbacks where we see helium enhancements. So these are the type of combinations that we're intending to do over the next decade. And as I said, these are just examples of this, what I think, exciting multi-messenger decade. In the next part of my talk, I'm going to be talking mostly about updates on DKIST, the Daniel K. Inouye Solar Telescope, and on GONG. Let me start with DKIST. Here you have images. DKIST is on the island of Maui. Here, this one over here. And this is a very recent picture of DKIST already doing on-sun campaigns. I want to emphasize that DKIST has not started regular operations yet. We are in the latest phases of construction, and I'll give an update on the status on the timeline for starting real observations. In this image over here that you can download from the National Solar Observatory website, you can already see something that is very peculiar and specific of the Daniel K. Inouye Solar Telescope. Solar light comes from here, and then the primary mirror sends the light to a site. So it's an off-axis configuration. The off-axis configuration is really crucial for the coronal observations, for observing the corona as I have been explaining. Not having the secondary mirror and the spider that on-axis telescope have on the beam will minimize the amount of stray light and will help us observe the solar corona. That's why it has this configuration, and it has many other components that help us observe the solar corona. Most important one is being at one of the best coronal sites in the world, which is the Hawaii Islands, and in particular Maui. Here you have some images of on-sun campaigns. DKIST is already pointing to the sun. This is the Kuder room, already fully loaded with instrument. I'll show another picture of those. And this is DKIST doing another on-sun campaign where you see the secondary, the heat stop, rejecting most of the solar light to a site. We only select the minimum fraction of the light that goes through the Kuder room and then is observed via the instruments. What is the timeline? COVID-19 has impacted the end of construction. The end of construction is now going to be in November 2021. We are 2 months from the end of construction. And at that time, we will start what we call the commissioning phase. Commissioning phase is going to last for 1 year from November 2021 to November 2022. But already during commissioning, we are executing observing proposals. We made a first call for observing proposals. We received 101 proposals. 50 of them were accepted by the time allocation committee. This is really a lot of proposal pressure. We are actually intending to make another second call for this 1 year phase, and that will be sometime near the end of this calendar year. That will make another call for observing proposals in the second half of the commissioning phase. DKIST is 4 meters, and I'd like to explain why. Of course, solar astronomers know, well, you always want good signal to noise. You want to observe the highest spatial resolution. And I'll give you more detail how do we get this 4 meter aperture, because I know for many of our nighttime colleagues, it's hard to understand that you need 4 meters for observing the sun, but I'll prove it in a second. You need 4 meters. DKIST has other properties. It's multi-line. It's able to observe multiple lines so that we can observe different heights in the solar atmosphere. From the beginning, we wanted to measure the magnetic fields with high precision, and that means we knew it was going to be polarimetry. So DKIST is designed from the scratch as an accurate and sensitive polarimeter. It's a very specific property of DKIST. And as I've been saying, it's also able to observe the solar corona thanks to this off-axis configuration and other properties. We are expecting to be able to see the solar corona half a solar radii above the solar limb. That's more or less the region that we're targeting for mapping the solar corona with polarimeters and with spectrographs. This is the slide that I like to use to explain that, yes, we do need 4 meters, even if it is the sun. And it is driven from the science we want to do. Here you do see a simulation. This is not solar observation. This is an MHD simulation that tells us that in some cases, these simulations predict the existence of a local dynamo. A local dynamo driven by turbulence, and this is these black and whites. These are these magnetic fields. I mean, if they are really there, this is a prediction from a simulation. We want to see them. We haven't seen them. There are indirect evidence for this type of magnetic field, but we have never observed them the way we observe the magnetic fields of a sunspot. If you want to observe the magnetic fields of a local dynamo, you're going to need a signal to noise of 10 to the 4. You're going to need to have a resolution of 0.1 arcsecond, and you're going to need to have 10 seconds exposure time. There are other science cases that need similar requirements. Here I have chromospheric magnetic fields. You'll end up with the same numbers, and solar physics is not here. If we do 10 to the 4, and we do 10 to the 4 signal to noise these days, you have several arc seconds spatial resolution and several minutes of temporal resolution. If you want to do 0.1 arc seconds and 10 seconds exposure time, then you'll have more 10 to the 3, even less than that. So solar physics is not here. And what is what you need to get to this parameter space? Take the same equation that nighttime astronomers use for understanding what is exposure time, given a signal to noise that they want to achieve, given a star with a magnitude, and a telescope diameter where you got observing time. Same equation, but now solve for the diameter of the telescope and put these numbers in here. When you do that, you get 4 meters. So for these science cases, we need 4 meters. That's why DKIST and also the European Solar Telescope is targeting these 4 meters aperture. And that's without talking about the solar corona, which is much dimmer, right? But so even for the on-disk observation, we need already 4 meters. This is the, sorry, I went too fast. This is the good room. Here you see all the instruments that are already there. This is the one we're going to be using for specific observations of the solar corona. It's a cryogenic instrument, again, to help coronal observation. Is observing in the infrared above 1 micron. This is the near infrared Stokes polarimeter. Then we do have the diffraction limited near infrared Stokes polarimeter over here, BBI, the visible broadband imager, and the visible spectropolarimeter in here, and the adaptive optics. We need to correct for the real-time errors that the Earth atmosphere is introducing. The correction is done by this system of adaptive optics. Right now, we only have one deformable mirror, but the team is already working on bringing 2 additional deformable mirrors, and we will be doing multi-conjugate adaptive optics. There's another instrument, the BTF, which is a set of fabric pearls. This is coming from Germany, and this will come next year. As you see, the instruments are already there, and they are already doing the science verification. Here you have the science verification of the visible Stokes polarimeter. And here you have precisely that, spectroscopy and polarimetry. Here you see spectral lines, the intensity, and the Stokes parameter over here. This is from the scientific verification of the instruments. Again, we haven't started operations yet. This is the adaptive optics thing with the wavefront sensor and monitoring and looking on different features on the sun. This is all ongoing. These are images from this year, and there are other on-sun campaigns as we speak. I've been emphasizing observing the solar corona to measure the composition. In particular, I've been saying helium. We want to observe helium and the abundance of helium in the solar corona. But really the main driver for the observations of the solar corona is to observe the magnetic field of the solar corona. And we're doing this with a number of spectral lines. Yes, this is the helium line that I was mentioning for the abundance of helium. But we have other lines. And of course, it's the million degrees solar corona. So what we have is iron-13, highly ionized species like silicon-10, silicon-9, silicon-11. They are all in the infrared. This is why we need a cryogenic instrument. And these are the type of lines that we will be using to map the magnetic field of the solar corona. We are here using 2 effects. Typically on this, we use the Zeeman effect. For observing the magnetic field in the solar corona, we will be combining the Zeeman effect and the Hall effect using forbidden lines. And what we're going to do is to actually map in detail one region, or sometimes we'll be using DKIST in a synoptic manner, where we will be mapping the entire solar corona regularly every day to get a full understanding of how the solar corona looks like. And we're going to use this type of data to validate coronal models. That's the first use that we can do with these coronal magnetic fields from DKIST, validate the coronal models that gives the heliospheric modeling that I've been showing during my talk. They start from GONG data, but then they produce a corona, and from the corona, they produce a heliospheric magnetic field. So you can test the validity of these coronal models. And one day, I hope we can use DKIST data to even drive coronal modeling. As I've been saying during all my talk, what we're trying to do always is to improve these connectivity models. How are we magnetically connected to the sun? And I think DKIST can play a specific role with this type of coronal magnetic field mapping. Let me now move on to GONG and the future of GONG. This is the station that is in Udaipur, India. We have 6 others. And I think by now you already understand that GONG is playing a role in this connectivity. Of course, this connectivity more the part that is related to space weather. And here you have another space weather prediction coming from the magnetograms from GONG. But what I like to emphasize always is that GONG, which is a 6-site network, was started in 95, and the idea in 95 was to do heliosmology. It was to measure solar oscillation, a very important problem about how the interior of the sun is actually moving, what are the flows in the interior of the sun. This was the main driver to build GONG the way it was. It was 26 years ago, 27, depending on how you count. But it was not intended to measure the magnetic fields. GONG started measuring magnetic fields only in 2006, and that was thanks to a minor modification that allowed to measure not only velocities, but also magnetic fields and started producing the magnetograph. This was a great development, is producing these space weather predictions, but actually what I like to say is that it was an afterthought. GONG was not designed with space weather in mind. And if we want to now do improvements in terms of the space weather capabilities, what we want to have is a network that defines what the properties are with space weather in mind, has a space weather requirements from the beginning. I always like to emphasize these days that for the operations on GONG, we're getting support from NOAA. This is the National Oceanic and Atmospheric Administration, in particular the Space Weather Prediction Center in Boulder, who actually has signed an agreement for helping the GONG network until 2026. But of course, the question is what comes next. Here you see one of these models for space weather that I've been showing during my talk for space weather predictions. And they are able to give us a lot of good information about the solar wind. But I have already said at the beginning of my talk that the situation is not fully satisfactory because we have these CMEs, and here you have another example. This is going to be another CME that is hitting the Earth. The Earth is this yellow dot over here. And as I said at the beginning of my talk, we don't know what the magnetic field was. We don't have a magnetic prediction for the CME as it arrives the Earth. These models do not include magnetized CMEs. Only the background magnetic field, Parker's spiral, is magnetized, coming from GONG. And we want to start having predictions of the magnetic field. This is what I like to call the missing problem, the BC problem. How do we start predicting how BC of the CMEs is going to come? Again, remember what I said at the beginning. It's really important whether the orientation of the CME magnetic field is parallel or anti-parallel to the magnetic field of the Earth to understand how important a given CME is going to be in terms of geomagnetic impact on the Earth. And actually, if you go back to the sun, again, looking how it all originates, we know where they do originate. We've been observing these filaments for quite some time. The filament is the black feature that you see here. Keep looking at it. All of a sudden, it's gone. Where is the filament? Where is this black feature? Well, the black feature is the dense core of the CME, and it's flying in the heliosphere, in the solar system. Now it's on the sun, and all of a sudden gets unstable. We don't understand the process. It produces a flare, and then it flies through the solar system. But I always like to mention this paper from 95. So it's not that 93, it's not that old, only a few decades, where it was saying, well, the solar flare myth, saying, well, flares are important, and solar physics has been observing flares for years. What is important is the CME. What is important is the filament, because this is what gets ejected, and this is what arrives the Earth, and it can potentially produce a geomagnetic storm. As I said, this is knowledge that we have had for only 25 years. And we need to concentrate on the CMEs, and we need to concentrate on starting predicting the orientation of the magnetic field when it arrives the Earth. Of course, that means propagating a magnetized CME. We're not propagating these magnetized CMEs. What we need to do that is the boundary condition. What is the boundary condition that will allow us to propagate a fully magnetized CME? Of course, you need to measure the magnetic field at the source region. You need to understand what the magnetic field of the CME is before eruption, and then propagate it with the magnetic properties. And what we now can do, and this is also a relatively recent development, is to map the magnetic field of filaments with high accuracy, measuring a number of spectral lines, doing a spectropolarimetric. And here you have an example of a filament that was mapped before eruption, and we know the entire magnetic configuration. What we need to do now is to do this in a synoptic manner. We need to observe all filaments on the sun, understand the magnetic configuration, and once there is a CME, give this as a boundary condition to propagate the magnetized CMEs. Is it possible to propagate magnetized CMEs? Because I've been saying that here we're not propagating magnetized CMEs. This is the operational model, but there is a lot of research going on for propagating actually magnetized CMEs. And here you have 3 examples. This is the team in Japan. They have a model called Susano CME where they propagated CME, a magnetized CME, and this is what was measured by ACE, and this is the prediction they made, the red line, after propagating a magnetized CME. Similar, this is from the group in California, in San Diego, where that's what was measured, and that was the prediction. I mean, it's not perfect, but they are starting to be able to propagate a magnetized CME. This is from the group at the University of Michigan, the awesome model, where you again have some measurements and then what was measured actually in situ. I've learned since I made this slide that there is a group in China propagating magnetized CMEs. There are other groups. There is a group in Europe, Euphoria, and even in the US at the University of Alabama. So it's getting more and more popular, and we're having models that are able to propagate these magnetized CMEs and tell us how busy is going to come when it comes to the Earth, parallel or anti-parallel to the Earth magnetic field. What is important is to give the right boundary condition. I've been talking to the teams here, and one of the things they need to improve a lot is on the boundary condition that they are using. Right now, the boundary condition is not magnetized, it's just some type of modeling that they do of what the magnetic field potentially could be, given some rules that are typical on the sun, like the hemispheric rules for helicities. But the question is, let's measure the magnetic field, let's measure the helicity, and let's provide this as input for propagating a magnetized CME. That's what we need to do. That's what we are aiming that the next generation GONG network will be able to do. We are working in collaboration with our colleagues from the High Altitude Observatory in Boulder, Colorado, where we want to measure, we're going to propose to the National Science Foundation this next generation GONG. It would be a similar network. It needs to be a network. And it needs to have this ability to measure the magnetic field in the photosphere, in the chromosphere, and in particular in the filaments, so that before the ejection occurs, we know that the magnetic field configuration, and we start predicting what the magnetic field near Earth is going to be. And with this, that's the end of my talk, and I'll be ready for answering questions if there are some. Thank you.
Thank you, Dr. Valentin. We now we open the floor for questions. I think Professor Shibu Matthew will conduct this question and answer session. We'll take the questions from WebEx as well as from YouTube.
Good.
I don't see any questions kind of typed on the WebEx. So if you would want to ask that question directly, then they can do that.
I do. I raised my hand.
Oh, okay. Where is that? Okay. Let me check. Yeah. Okay. You can go ahead.
So shall I go ahead?
Yeah.
Yeah. Okay. Hi, Valentin. Very nice talk. Thank you very much.
Thank you.
Yeah. So I have one question rather at your last point about CME propagation. It's indeed very nice development that now people can actually follow the magnetized CMEs. But I guess you would need further more information about that in addition to just following their evolution, because there will be 2 or rather 3 factors, because the way the prominences evolve, we know that depending on what sort of topology in the nearby regions are, you could have different kind of eruptions, like only top part goes or side goes, and that will carry a completely different magnetic field information than we would get from the whole prominence magnetic field. And then the second thing would be that when we are measuring at, for example, let's say at L1 point, we'll be measuring at one particular location, right? So at that particular point, maybe the BZ is not reflected the way we would like it to be. So do you propose to have multiple spacecraft measurement at, for example, Alban Point from different directions to figure out that what CMEs are going to be space weather effective?
Yeah, thank you for the question, Durgesh. I mean, let me say, this is a very, very complex problem. It has many components. So I'm going to try to answer what you are asking. What I want to emphasize is that no matter how complicated it is, what we know is that we need to start propagating magnetized CMEs.
That is the first thing, correct? Yeah.
Right. So we all should agree. Let's start propagating magnetized CMEs. Enough of propagating unmagnetized CMEs. Yes, we didn't have anything else before, but we now need to evolve into that direction. So many things are needed, and you are totally correct. It's not only the magnetic configuration of the filament region, it's also the environment corona. How is it? But we're doing coronal modeling. So from the regular GONG data, we do some coronal modeling. We probably want to move into vector magnetic fields, so we do more complex, nonlinear force-free coronal modeling of the entire solar corona. And then we know whether the filament has a nearby coronal hole, it has an active region, because we know that can change the direction of the CME. Totally right. So we need to also improve coronal modeling, not just give better boundary conditions of the filament. And then the propagation has a lot of physics. How it propagates from the sun to the 1AU, it has a lot of physics. We probably want to do data-driven. I'm of the opinion that we probably want to have the entire heliosphere filled with buoys, with magnetometers. That tells us how the magnetic field is propagating, and we, like what regular Earth weather people do. They have sensors all over the Earth, and they feedback all this modeling into your models, all this data into the models. We need to do something similar for space weather. So it is really a very complex process, but we need to start going in that direction, because we now know that this anti-parallel configuration is really what creates the very dangerous conditions, the Carrington type of events. We don't know if Carrington was a negative BC, but it probably was. Right? So yes, there is a lot of developments. What I'm trying to indicate is that also improving on the boundary conditions is going to be crucial. So last thing that I'll say is that, you know, these models that I showed, the ones done from Japan, in the US, they assume some helicity. What is the helicity? How do they infer whether the field lines are going in that direction or in the opposite direction? This is just from observing the magnetogram, the shear, and they should be right-handed or it should be left-handed. I'm saying, let's measure it. And let's, even the number of helicity, how helical the field lines are. Let's give the field lines and let's start putting this into the model and let's propagate the magnetized CME. It is a very complex problem. Absolutely.
Yeah, indeed. Thank you. Thank you.
Yeah.
Dipankar, yeah, you can go ahead. Yeah.
Thanks, Valentin. This is Dipankar here. So I have a couple of questions quickly. Of course, always about switchbacks. So you mentioned that the switchbacks are carried to the solar wind. So and also the supergranular scales are being detected. So my question is, how far you expect them to be, you know, keeping the same kind of supergranular scales, because there should be possible expansions and so on. And a related point is that if you say that they're still, the switchbacks are still preserved as they are carried with the heliosphere, I mean, isn't it that, you know, the stretching and something you would also see, so that, you know, the same switchback properties, which was probably because of interchange reconnection close to the sun, may not be preserved. So then the related point is that probably switchbacks can happen also in the solar wind itself. So how do you rule out?
Right. No, we cannot rule out that switchbacks do occur in the solar wind itself. There are theories where there are shear between different flows, and then you create a switchback. And, you know, as always, probably all of these explanations are happening on the sun. The region where these two papers, and these two papers are impressed, I just learned about them the other day and I was excited, are saying that they do see the footprint of these supergranular scales and even in one case the granulation. So of course I think the relevant one is this supergranular scale. This is where in the supergranular is where the network concentrates, is where all of these reconnections are going to happen. So we were expecting that it would be there, and they found it at least in 2 papers. Now, they have found this in the region where Parker Solar Probe is now flying, which is typically between 20 solar radius above the solar limb and 30 solar radius. That's the region where they found it. The switchbacks were known even before Parker. They were found in Ulysses, but there it was impossible to see a large number of them and even try to correlate with anything on the sun. Then getting closer to the sun helps you understand how things originate. I think the important thing is going to be solar orbiter. Solar orbiter now is going to measure these same magnetic fields much farther. So we'll see the region that is not as close to the sun. Also, Parker has some data. We'll see, but I don't think there are studies about when do you stop seeing that many switchbacks as you get farther and farther from the sun. And the prediction about probably you need to see less and less as you get closer also to the sun. So I think it's exciting times. We just need to wait to all encounters of Parker closer to the sun, how solar orbit is going to be able to provide additional coverage of radial distances, and how frequent the switchbacks are. I must admit I'm a little biased towards they originate in the solar atmosphere. I love the idea that something like the interchange reconnection that was proposed decades ago, it was proposed for something that is needed for the solar dynamo. This type of interchange reconnection would be helping even the polar reversal. So we were expecting something like this being there. And now if we're able to link it to something as fundamental as what the switchbacks seems to be close to the sun, I think is exciting. But yes, we should not rule out the creation of switchbacks from the evolution of the solar wind.
Thanks. Shibu, can I ask another question? Yeah, sorry, Shibu is silent, so I take it as yes. But this is about the polar map, coronal map. What you said, not polar, coronal map from the DKIST with infrared lines. Why I'm asking this question, as you also know that Aditya will be also doing such a map, so it will be very, very important for us to do things as a joint campaign. Now question is, how long does it take for such a map from DKIST? Because the DKIST has a much smaller field of view, so if you really want to create a map, you need to sort of have a mosaic. So how long does it take for that mosaic?
It takes a long time. And yes, we need to collaborate because I know that actually you are going to be using from space the forbidden lines, same as us. So yes, let's keep close contact. Let me say one thing. This is really unexplored territory. Nobody has really done that. I mean, there is COM from HAO that does forbidden lines linear polarization. But here we're including Zeeman, Stokes V. And for that, you need to integrate for long times to be able to get the signals for the linear polarization, Hall-effect, like COM is doing. And we also want the line of sight regular Zeeman effect from these forbidden lines. How long is it going to take to do one of these maps? Really, in what we're planning to do is something like this. There would be a synoptic program for DKIST, which needs to be approved by the time allocation committee, by the way, that will do in the afternoons some of this mapping. One of these is going to take 1 hour, just one of these positions, one of these circles. That's the field of view. And just mapping this, it'll take 1 hour. It really depends on the sensitivity you want. So it might take even longer. But one of these with a regular for an active region, like the one you have here, we're talking about 1 hour. So doing this does require multiple days, meaning that all we can aim at doing is a type of a synoptic type of coronal magnetic field mapping that is 1 month, integrated over 1 month, okay? Like the regular synoptic map. But of course, I mean, you would like to have something faster, but there are not that many photons in the corona, and there is nothing that can compare to this unless but yes, we need to start doing this from space, and I'm totally excited to see the Indian satellite flying and doing this. Let's see what we learn from from DKIST and how we can coordinate.
Thank you. Thank you very much.
Yes.
So maybe Ambasaji is the hand, so he can ask the question, and then we will go to the chat box and then take the remaining questions.
Yeah. Yeah, hello, Valentin. This is Ashok Ambastha from Udaipur. Can you hear me?
Yes.
Yeah. So actually, my question is regarding another aspect of solar physics, which we expect to be dealt by these new instruments which are coming up. So far, we have been talking of GONG instrument for helioseismology, also STO to some extent. After GONG, with this, Inouye telescope, the resolutions are going to be improved much more. So I'm just wondering, you did not touch upon this helioseismology aspect, especially the local helioseismology, where one would like to see underneath the photosphere, which is not possible so far. So I was wondering whether this will be one of the aspects to be dealt with or no.
Yeah. So you're talking about doing local helioseismology with the highest resolution possible.
Yeah, in order to have extend, the L range to the higher L, so that one can probe underneath the photosphere.
Let me give you an answer here. I've been talking to an expert. I'm not an expert on helioseismology, and I've been saying, well, in the same way that we know sunspots do interact with P modes, and we measure these mode conversions in sunspot. Can we do this for flux tubes? Can we do this for the smallest scale structures? And I never got a good answer. So if you can give me a good answer, I think the idea is, if there is science to be done here, put a proposal for DKIST and submit a proposal for doing local helioseismology at the best possible spatial resolution. But when I've been asking my helioseismology colleagues, I never got a clear answer whether helioseismology for structures that are 100 kilometers size, flux tube, this would make much sense. But maybe we're missing something and there is science that one can do, and then the best is to submit a proposal. So I would turn the question to you. Do you think that yes, at the scale of flux tubes, of these small scale structures, there is good local helioseismology to do?
Yeah, I think so, because a lot of physics which is related to the flux tubes is actually not done so far, in terms of local helioseismology. So I think it will be a good science. I'm not sure. Earlier I had some feedbacks from Frank Hill, but I have not been in touch with him for some time. So
he's around.
And
I talk to him every now and then.
Yeah, please. Yeah.
No, just one thing. I mean, I think for what you are saying, I would say just submit a proposal to DKIST. I think the instrument you would need to use is BTF, the German instrument that is not available yet. You should wait until it's there. And once it's there, submit a proposal.
Okay, thank you. The other thing is that about this 1080 polarimetry, which you mentioned in your talk, I'm not sure exactly at what resolution you will be able to get the magnetograms in 1080, and what will be the sensitivity of measurement?
So DKIST is going to do 1080 polarimetry, and it can reach the best spatial resolution ever achieved for this line, which would be below 0.1 arcseconds. But I think you're referring more to when we do it with GONG, with the new network, where we're going to do helium 1030 polarimetry for all filaments. For GONG, what we want to achieve is something like 1 arcsecond, similar to HMI. We don't want to target, I mean, you cannot have a network of DKIST on the wall, but you want to be able to measure the helicity. As I said, when we propagate the magnetized CME, we want to see in detail the helicity, how much helicity there is. And for this, I think with 1 arcsecond, we can give good input data for the propagation of magnetized CMEs. So with GONG, we are targeting more of a 1 arcsecond resolution. This is actually same as MAST in Udaipur. mass would achieve something similar. And it can start playing a role on this by measuring magnetic fields of solar filaments. And then, of course, with DKIST, we would be achieving 0.1 arc-second resolution or better.
Okay, thank you so much. Thanks.
Yeah.
So shall we take up the question from the chat box now, because there is no raised hand here. So Divyantu, he was asking a question about how do you separate the spatial and temporal variations of the switchbacks from the in-situ measurements? Why switchbacks are enhanced in helium?
Yeah, good questions. I am slowly learning about how they do all of this, so I have the same questions myself. I'm going to answer partially some of them. Let me go back to the slide. You should keep in mind that they are not only measuring the magnetic field, they also measure the particles that are propagating through those field lines. Through the combination of the particles and the properties of the particles, the suprathermal electrons, and the stroll of the particles, they are convinced that what they have is an actual bending of the magnetic field line. This is all explained in these two papers. These are Nature papers from 2019 from Stuart Bale and Justin Casper. Justin Casper is the PI of the solar wind instrument, and Stuart Bale of the magnetometer. And the two papers explain, no, these are bending of the magnetic field lines. This is not a confusion between time and space because of the motion of the spacecraft. So I invite you to go there and read it. It's, again, combining both the magnetic measurements and the properties of the particles that are measured by Parker Solar Probe. And then about the helium, I cannot give a more detailed answer. About the helium enhancement. You know, the idea is the following, and I didn't say that during my talk. So this is an open field line. So this one is carrying out the regular solar wind. And depending on the velocity, as I said, it will have more or less helium, depending on how fast it is. So this is already carrying the solar wind. All of a sudden, you are connected to a closed loop from deep into the atmosphere. So the abundance of helium here is expected to be the photospheric abundance. It's not reduced in any way because it's not part of the solar wind. As I've been saying in my talk, the solar wind depletes helium, but this one is fully loaded with helium at photospheric abundances. As soon as the reconnection occurs, you expect the photospheric abundance to be present here, while the rest of the magnetic field is carrying the solar wind abundance, which is lower helium. That's the idea. That's why it is important that we are able to confirm these changes in helium abundances also with remote sensing, because this part in here will be loaded with these photospheric abundances. And again, it's another indication that probably this is happening deep into the interior, because all of a sudden, deep in the solar atmosphere, because all of a sudden in the switchbacks, you find photospheric abundances, not the regular abundances in the solar wind that are depleted of helium.
Okay, and the next question, Ankit Kumar, he's asking what are the difference to study the sun in the domain of wavelengths and particles? Does the study in both domains provide the different or same properties of the sun?
Yeah, let me go back to another slide. I probably should keep them. So wavelengths are, I understand that the question refers to telescopes. By observing different wavelengths, what we do see on the sun typically is different heights. And I'm just going to the solar orbiter case, but you can think of telescopes on the ground, you can think of DKIST, you can think of MASS, you can think of any of the other telescopes that we have. And by wavelengths, we're going to be doing remote sensing and observing different heights, but all of them relatively close to the sun, of course. If you go to the X-rays, you'll see the hot corona, the 10 million degrees solar corona. But by particles, what you measure is where the spacecraft is. What you measure is the extended atmosphere of the sun. So again, what you're doing is just changing the distance to the solar surface of what you are measuring. This one is closer to the solar surface with wavelengths, and with particles and in situ measurements is farther, but still close enough to be able to isolate one single event on the sun. Again, as I've been saying, the problem at 1AU is that at 1AU, you are impacted by multiple things occurring on the sun. What you measure at 1AU in situ with particles is coming from multiple places on the sun. It's hard to isolate. You need to get a little closer. That's what Solar Orbiter and Particle Solar Probe are doing, to be able to say, okay, I measure a lot of particles and they're coming from there. And then you go with the telescopes and you observe whatever you see there, and you try to relate one to the other much better than what you can do at 1AU. I hope I have answered the question.
I think so. Yeah. So he's not saying anything. So, so next question is from Bhaskar Mukherjee. What he is asking is, can we predict solar wind characteristics from ground level neutron monitoring?
Yeah, the neutron monitors are an a signal of the solar wind. They are of the way we interact with the solar wind. There is a network of neutron monitors around the world, and probably people at PRL are more familiar than what I am. But yes, that the neutron monitors on the Earth are actually indicating us what the solar wind is and the strength of the solar wind, or even whether we get a CME. So the two things are related. Again, what is important here is to improve the magnetic connectivity modeling. And when I say magnetic connectivity modeling, what I'm talking about is space weather predictions. When you say magnetic connectivity modeling is in general over the entire heliosphere, what happens in Mars, in Jupiter, but for space weather is connectivity at the Earth. So what I've been trying to present here is mostly how to improve that modeling. And the neutron monitors will also be able to confirm that we are making improvements on that modeling if we're able to predict what the neutron monitors are going to measure.
Yeah, okay. So with the next question you can take. So Bijoy Dela, so he is asking, is there any possibility that switchbacks are responsible for acceleration of super thermal particles in the interplanetary medium during the quiet periods?
As far as I know, my answer is that I haven't seen any indication that they are related. But I would invite you all to go to these papers. And what I would do is actually look at all the citations that they are having. They are highly cited, the two of them. These are the two that describe the nature of the switchbacks and use the citation of ADS to see if there is any indication. I don't know of any, actually.
So the next question is from Hariom Pats. So he's asking, solar maxima are continuously low. Are we heading to solar minimum, and what possibly will be the implication?
Well, I think the question is about the prediction of the solar cycle. That's the only figure where I have some solar cycle information. We're entering solar cycle 25, and the prediction is just going to be a little stronger than 24, a little. And then there are other predictions, but this one that says it's going to be a little stronger than 24 comes from measuring the strength of the solar poles during solar minimum. And we actually think this is the best indication we have for understanding what the strength of the next maximum is going to be. So we've gone past solar minimum, we've measured the strength of the field during solar minimum, and that tells us that we are not entering into any type of Maunder minimum. We're going to have a solar cycle that is going to be a little stronger than 24. Not really one of the strong cycles, but a little stronger. Now, I'm going to use this question to say something that I haven't said, which is, I was emphasizing, we're missing this part of providing boundary conditions for propagating magnetized CMEs. That's one of the things we target with NGGON. With NGGON, we're also targeting much better measurements of the poles because, for example, the poles, the strength of the solar poles at minimum tells you how strong the next maximum is going to be. how is GONG going to do a better job at measuring the poles? The poles are hard because you are always having a huge perspective effect. But one of the things we need to improve is our sensitivity to transverse magnetic fields. The poles are at 90 degrees from our line of sight. So most of the fields of the polar caps, as seen from the Earth, are transverse. And our sensitivity to transverse fields has always been historically very bad. We are trying to improve that sensitivity, and this is the reason why we are convinced that GONG, much more sensitive to transverse fields, will be able to do a much better job in terms of mapping the polar fields during the entire solar cycle than what we can do with GONG today. How is GONG doing at measuring the polar fields? It was never a requirement. As I said, it was doing velocities, and then we put a halfway plate and we changed the halfway plate and we started measuring magnetic field, but it was not a requirement. With GONG, we are targeting a network that should be able to give high sensitivity transverse fields and then better measurements of the solar poles.
Okay. So maybe, okay, just Rajguru, I think he just want to know the timeline for the GONG.
Yeah, so the timeline is not clear. Right now, all we have is a proposal together with HAO to the National Science Foundation. We also think we need to talk to other stakeholders in the US, like NOAA, to see what their interests are in funding such a network, the design and the construction and the operations. But I want to say that this is also an international project. We are open to international collaboration. We've been discussing with people that have an interest in Europe with the SPRING project, and we would have an interest, of course, in talking to partners in India if they have an interest on participating in the design phase of GONG. All I can say is that, as I mentioned, NOAA is now funding GONG for 2026. So we know we are funded until 2026. We would like to see progress on GONG beyond 2026. It should be in between 2026 and 2030 that we actually replace GONG with GONG. GONG is aging, is more than 25 years old. So it is urgent that we start working on replacing a GONG network. One thing that if NOAA uses GONG is because they don't want to use satellite data, or they want to have a backup for satellite data that can be impacted by space weather conditions. So if satellites are switched off during space weather events, they don't want to see that, and they think a ground-based network is much more robust. That's why NOAA emphasizes ground-based magnetograms. That's why we want to have a replacement for GONG.
Kamalesh Bora, she's asking, is interchange reconnection found always in near neighborhood of coronal pole?
Yeah, good question. I mean, interchange reconnection is still a hypothesis that you have in here. What we measure is cancellation. We observe cancellation, but we only observe cancellation typically at one height. There are very, very few studies where you can see different heights. And from this image, you'll see how important it is to be able to map what it is in here. Here you'll see the cancellation, but what it is higher up, so that you are more sensitive to these other structures as you move to higher layers. So interchange reconnection is still a hypothesis. It's a nice case. There are theoretical modeling. There are indications, as I've been talking, that is happening. Where does it happen? It happens for sure where there is a lot of network concentration, which are at the supergranular boundaries. But yes, the idea is that in coronal holes, what you have is a lot of these open field lines. But the question is, do you have also inside the coronal holes this population of closed loops emerging in coronal holes? I think the answer is we don't know. We need better sensitivity to see what the density of closed loops are in coronal holes to say inside coronal holes you do have interchange reconnection. That's another target for high sensitivity, high resolution, like DKIST studies, where it's okay, well, we've seen this. We know coronal holes have these unipolar fields. Do they have also the bipolar, small scale loops that will lead to interchange reconnection? So this is why people have said, well, we don't know that, and where it can happen is at the boundaries of the coronal holes, but that's just because the boundary of the coronal holes, by definition, is going to have a lot more other polarities, and then yes, maybe interchange reconnection is more likely to occur there. Can it occur inside a coronal hole? Again, we need to see what the density of this type of closed loops are inside the coronal holes, for which you need high resolution and high sensitivity.
So there is another question by Beener. So what she's asking is, what are the initial parameters for CME forecasting other than helicity of the magnetic flux rope at the sun, which are used to understand CME propagation through the interplanetary medium? Okay, they have
right.
So, further, can these models account the fast solar wind CME interactions?
So could you repeat the last question?
Yeah, okay. What she's asking, the last question is, further, can these models account the fast solar wind CME interaction?
I would invite you to read these papers in here and see what they are doing, what hypotheses they're putting, and how good they get into propagating the magnetized CME. As you see, still kind of poor. I mean, here you get this positive BC and then the negative BC, and that's actually what is observed, but later and at different amplitudes. So if you really want to know how good they are, and these are all recent work. They are putting more physics on this work, and you need to go to the papers to see really how good they are. I don't think they are as good as to predict the fast CMEs near Earth yet. Here you can see some of the boundary conditions that they are using for propagating a magnetized CMEs. So it's very parameterized. There is a helicity, and there is a magnetic flux of the flux rope. But then there is all these geometrical numbers. So they have like 7 free parameters. One is the helicity, one is the flux of the flux rope, and then this distance from the center, these other components of the flux rope, but it's very, very simplistic. We are in the early stages of this type of modeling.
Okay. Shall we take the next question? I think Deepankar, you want to ask a question? Hello.
I think, yes, there is a question on the chat, which is there any relation between magnetic flux cancellation and magnetic reconnection? This is actually a very, very good question, because we observe magnetic cancellation. Is magnetic cancellation always magnetic reconnection? We don't know that for sure. If you have submergence of a closed loop, you see two polarities getting together, and all they are doing is submerging. So this is another area where we will need high resolution, high sensitivity, in particular to the transverse fields as the loop submerges. We haven't seen these transverse fields submerging, and we need to distinguish between when cancellation can be reconnection or submergence.
Durgesh, you want to ask a question?
Yeah, it's rather a comment, Valentin, than a question. So this is related to the question asked, like, does the interchange reconnection happen only at the boundary? So there is a paper by Vyakhyaan and Solanki in 2004, where they looked at the density of loops in coronal holes and in quiet sun region, and what they find that in the coronal hole as well as in the quiet sun, the number of short loops are very similar. Whereas in quiet sun, you have longer closed loops, and in coronal hole, you have open loops. And that is the reason they give that when you look into the chromosphere and transition region, for example, you do not really see any difference between coronal hole and quiet sun visually.
I see.
the coronal holes start appearing different only in the coronal lines.
Yeah, I see.
And he just looked at, so used that statistics and looked at silicon 4 lines in iris. And what we found that though visually at that level, you don't see much difference in the intensities, but when you look at as a function of magnetic field, that, going from a small scale magnetic field to the larger strength magnetic field, that essentially going from internetwork to network region where you have large clumps of field, then with the increasing strength, you start seeing more and more differences in the intensities, as well as the Doppler shift pattern changes. So you start seeing upflows and downflows in quaternion and coronal hole differently. So what we feel that all this reconnection with the small scale field in the coronal hole with the open field, that will give a switchback plus a Doppler shift, which is making the plasma flow along the solar wind. While in the quiet sun, the reconnection will happen in closed field lines, and that will give you all the intensity bound within the closed loop. So I just sent you an email with the paper that you might find interesting. But what you said will be really nice to be done with the very high resolution to actually work out the number density of loops in much more detail and figure out what they are.
Absolutely. That's what we need to do. That's a good target for DKIST to understand better the density of closed loops at in all regions, but including coronal holes, of course. Yeah, good point. Thank you.
Okay. So there are two more questions maybe in the chat box. So Harshida Gandhi, he's asking about predicting CME arrival with a good lead time is very crucial on Earth. In your opinion, what do existing prediction models lack?
Yeah, I think this type of modeling doesn't have a magnetic field, but it is done for predicting arrival time. That's the main target of this type of modeling and why it is operationalized by NOAA Space Weather Prediction Center. And the arrival time they don't do such a bad job. I mean, it's not that they always get it right, but they do a good job in terms of saying when is it going to be. I mean, in terms of one day, errors of one day, they do a good job. So this type of modeling that is called sometimes ballistic, it's only using from I didn't say, this is data from Soho-Lasco, where you see the CME and they study the shape and the speed of the cone. Here you see the cone, and from there they model this, but they don't put a magnetic field. But they do a good job in terms of arrival time. But what we know is that the more physics we put, the better it's going to be in terms of predicting better arrival time. And again, the basic physics ingredient in this type of modeling is the magnetic field, the interactions with the environment in the corona, and the interactions with the magnetic fields as it propagates in the solar system. So even for improving on arrival time, I think it's important to start modeling this properly. It's a magnetic problem. It should be modeled with magnetic fields.
So there is one more question. The last question, I think, the chat box. So is there any solar proton detector AP9 model installed in Parker Solar Probe?
Yeah, so absolutely. So the instrument from Justin Casper from the University of Michigan measures electrons, protons, and alpha particles. That's pretty much what it measures. So the alpha particles is the helium abundance in the switchback that I've been talking about, but it measures electrons and protons. And then in solar orbiter, you have electron, protons, alpha particles, but you also have a heavy ion sensor. So it's able to measure these other highly ionized heavy ion species that are measured with a spectroscopy by SPICE. So yes, absolutely. There are proton detectors in both Parker Solar Probe and Solar Orbiter.
Okay. So there are no more questions in the chat. Well, I just have a question about the switchback. So how you really going to connect the switchback back to the something happening on the solar surface or combosphere or wherever? So you're observing the switchback with the Parker, right? And then you are trying to connect that with the so like this. So you're
again, this is a cartoon, right? And the question is, how can we confirm this cartoon?
Yeah.
Well, type of things we've been discussing, the density of these closed loops in coronal holes, which by the way, coronal holes is when Saul Parker is connected to a coronal hole is when they see the higher density of switchbacks. So it's going to be important to see how many cancellations, the density, the areal density, and the frequency of occurrence of these cancellations and compare with switchbacks. It's going to be statistical. It's going to be really hard to
That's what I was.
identify one single event that you say, okay, that single event is that switchback. But it's going to be all about comparing statistics. And that's going to be by measuring the coronal hole on the disk. But then, and that's probably what we'll see how well we can do in this type of configurations. Can we measure with either or with both, with solar orbiter, with DKIST, fluctuations in the amount of helium that we see as we propagate the solar wind in when we measure the corona? Can we map the solar corona and see local fluctuations that tell us, well, these are the type of fluctuations we would expect from a switchback? Are we going to be lucky enough? I mean, it is highly speculative what I just said, but we need to try.
Shibu, I have a question.
Yeah,
Can I
okay. Yeah,
ask?
yeah. Then you can.
So, Valentin, so what's your opinion about the source regions of stealth CMEs? Do you think that DKIST observations will help in providing some promising observation results on the source regions? Or do you think that, as some of the authors believe, that stealth CMEs originate really a little higher in the corona so that they don't leave any disk signatures behind?
Yeah, I really don't know. I think what I can say is that because DKIST can observe the corona, we probably can distinguish between the two theories, again, in a statistical manner, because when we're observing the corona, we're not observing on the disk and vice versa. I don't know for sure. We can discuss the properties. It really depends on the requirements of making this distinction and whether our instruments can achieve those requirements. Let me say one thing that I didn't mention. Cryo-NERS, the coronal instrument, the main coronal instrument is here. This instrument is a standalone. When you use this one, you're only using this one at DKIST and you're observing the solar corona. When you are on this, then through adaptive optics, you can use the combination of all of this and also BTF once it's there. So when you're measuring on the disk, you're not measuring the solar corona. I mean, with DL-NIRS, you can do some small tricks to observe both, but the main coronal instrument, and which is what you want to use for faint type of structures, you'll be using just by itself. So I would say I've been emphasizing the coronal aspects of DKIST. I think it enables totally unexplored territory, but there is a very steep learning curve. I would invite you to follow this, what the capabilities are, and if you see that, yes, probably we can distinguish, we can see which one of the two hypotheses is more relevant here to submit a proposal. But really, the coronal aspects of DKIST is where we're going to be learning a lot starting in November.
Thank you.
Okay.
Sure.
Maybe over to you, Nanda.
Okay, I think we had a very exciting question and answer session today.
It was good.
Thanks.
It was really good.
As we approach towards the end of the session, I have a very pleasant duty and a matter of honor to present a vote of thanks for today's Vyakhyaan to Dr. Valentin. And this, as I said in the beginning, this was organized on the occasion of Foundation Day of Udaipur Solar Observatory, which was on 20th September. So let me, first of all, on behalf of PRL Ka Amrut Vyakhyaan Committee, let me thank, and also on behalf of Director PRL and my colleagues, let me thank our distinguished speaker for an excellent Vyakhyaan and taking all the questions. I think we had more than 40 minutes of question and answer session from the audience. So we are very grateful to you, Valentin. It was indeed our pleasure to hear your lecture, and we hope that our partnership that was initiated in 1992 with GONG will continue and will strengthen further in the area of ground-based observations. and also with the kind of cases that you discussed with multi-messenger topics. So that is also we are looking forward to. Next, I would like to thank our director PRL for his full support to organize this 8th Vyakhyaan as part of the Foundation Day celebration of USO, and also to give the welcome address today. I would like to thank the Dean PRL and all the committee members of the Amrut Vyakhyaan committee for organizing and conducting the sessions very smoothly. Lastly, I would like to thank all the members who have joined us live on the for this Vyakhyaan on WebEx and also on YouTube. Before we close this session today, I would like to announce that next week on Wednesday, at the same time, we are having another interesting Amrut Vyakhyaan by Dr. Kazuo Shiokawa. He's from Institute for Space Earth Environmental Research from Japan, and he'll be talking on dynamics of aurora and air glow. So with this, I would like to conclude the session. Thanks to all of you for joining.
Thank you very much, and I look forward to visit Udaipur.
Oh, definitely. So
Yeah,
anytime.
you're most welcome.
I'd love to do it soon.
Anytime.
Thanks, everyone. Very interesting set of questions.
Yeah.
Very
Thank
good.
you once again.
Thank you. Thank you.
Bye.
Bye-bye.